In this video, I will be explaining bias-variance trade-off. The objective of this lesson is to understand the errors in prediction and classification models. So this is applicable to both models, and that's why it is a general topic. We have seen that the purpose of machine learning model is to predict or classify the output variable y from the given input variables, which are more than one, sometimes x1 to xn, and the function that is used is called as the estimating or predicting function, and it is also known as the model. And we have seen that the actual value is the sum of estimated value plus some error, and this error term is called as irreducible error, and this irreducible error is not dependent on the given input data set or the independent variable, and that's why it is called as the irreducible error. It is not dependent on the given data set. The second type of error that we are more interested in is called as the reducible error, which is dependent on the given input values x1 to up to xn, and we can reduce that kind of error by using some mechanisms that we are going to see, and those kinds of errors are called as the reducible errors. The one way of measuring the reducible error is by using what it is called as the mean square error. The mean square error is the difference between the actual value and the predicted value, and we are going to take its square. Means that why we are going to take the square? Sometimes the predicted value is greater than the actual value. In that case, it is the negative one, and sometimes it is the predicted value is less than the actual value. In those cases, it is the positive one, and we want to make the both situations the positive one, and that's why we take its squares, and then we take the square of the average, and that's why it is called as the mean square error. This mean square error is nothing but the reducible error. This mean square error is measured on two different data sets. The first is called as the training data set, that is the data set that we have used to develop the model, and the test data set. The test data set are the data set of the unobserved data points, and for that we want to use the model to predict or classify the data points. This mean square error, there are two different sources of mean square error. The one is the data set, as we have seen that the reducible error depends upon the data set that we use and the function that we use. And there are two different sources of the errors are that the data set itself and the assumptions that we made during the model development. We have seen that while developing the model, we make many assumptions. In case of simple linear regression or the multiple linear regression models, we make the assumptions what it is called as the linearity assumptions. Means that there is a linear relationship is present between the independent variable and the dependent variable. So this is one example of a assumption. The second type of example of the assumption is that we normally we make the assumption that the data set has the normal distribution or the Gaussian distribution. So that is the second example of the assumptions. And due to these assumptions, some errors comes. And the errors that comes due to these kinds of assumptions are called as the bias. And the errors that depends upon the data sets that we use to train the model and to test the model. So that kinds of errors are called as the variance. The variance is the error that depends upon the data set. Those kinds of errors are called as the variance. Now here I would like to further explain the difference between the bias and variance. And here I am using the scatter plot to explain the difference between the bias and variance. See, in here there are three different diagrams are there. This first diagram is I am referring it as the A diagram. The second graph I am referring it as the B graph, or the third graph I am referring it as the C graph. Let us concentrate on the A graph. In the A graph, we are making the assumption that that is called as the linearity assumption. In the linearity assumptions, we are making the assumption that there is a linear relationship is present between the independent variable and the dependent variable, and when we develop the model by making this assumption, we plot a our objective is try to find a line which is passing as close to as every points, and then we measure the one way of measuring the quality of this model is to measure the error between the actual value and the predicted value like this, and we tries to minimize this error. So here in the first diagram we are making the assumptions called linearity assumption. Now let us concentrate on the C graph, and now what we are doing that we are making no assumption. We are relaxing the assumption or making the no assumption, and in those no assumption we are trying to plot a graph which passes each and every point so that the error can be minimized. Here no assumption is there. So when we train the model without no such assumption, and we are trying to develop a graph which is passing through each and every point, we make it a low, what it is called as the low training error. That is the error that is measured during the training. So here it is a low training error is there. But when we measure the error on such kinds of model, we get a high training error or high test error. So here the error during the test is greater than error during the training, and that's why there is a large variation is present between the training error and the test error. So this situation is called as the high variance. But if we check for the first graph, that is the A graph, the error that we measure during the training is approximately equal to error that we measure during the test. So that's why there is no variance, low variance is there. But high error is present, and that's why it is called as the high bias. So this situation is called as the high bias situation, and this situation is called as the high variance situation. So the B graph, that is the ideal graph or the golden middle between the high bias and the high variance, is that we want to find a model or a curve which is passing through each and every point, so that we will have a low bias in which we are not making any assumption like the linearity assumption, and also the low variance. Low variance means that the training error, that is training error is, and the variation between the test error is both are same. No variation is there between the error that we got during the training and the error that we got during the test phase. So this is the golden middle point. So this situation is called as the low bias situation, in which we are not making any assumptions of the linearity, and low variance, because the difference between the training error and the test error is minimum. So that's why it is called as the low variance. So this is the golden middle. So these are the three different situations. But the point is that when we are going making assumptions, we get high bias, and when we relax the assumptions, we get a situation in which low bias is present but the high variance is there. So this tension between the bias and variance is called as the bias-variance trade-off. This is the tension between the bias and variance. We are trying to making the minimum assumptions. We get the high bias. When we tries to minimize the bias, we get the high variance. So this is the tension between the bias and the variance. So this tension between the bias and variance is called as the bias-variance trade-off. Another name that is given to these three different situations in terms of the fitting of the model is called when we get the high variance situation in which there are no assumptions are there. No assumptions about the linearity and like that. So that situation is called as the high variance, and that situation is also called as the overfitting. Overfitting means why it is overfitting? Because our model is trying to capture each and every points. So that is called as the overfitting. Then in the case in which there is assumptions are there, assumptions like linearity, and we get a situation called high bias, that situation is called as the underfitting. Why underfitting? Because the model is not passing through any one of the model or the minimum number of points. So that is called as that situation is called as the underfitting. But the ideal case is the low bias and the low variance. Now, here, how to recognize the situation in which low bias and high variance is present. So, if you are getting the underfitting situation is recognized when you get a high training error as compared to high training error as compared to the testing error, and the testing error is close to the training error, that is the symptom, or that is the indication of underfitting or high bias. If you are getting very low training error but very high, the difference between the training error and the test error is very high, that situation is called as the high variance situation or the overfitting situation. So these are the symptoms, and the symptoms of the low variance and the biases. So, and this bias and variance is applicable to both kinds of problems, regression as well as the classification problems. There are some remedies are available to overcome the high bias and high variance situation. If the situation is high bias situation, then you can develop, rather than developing a simple model with simple assumption that linearity is present between the independent and the dependent variable. Instead of that, you can assume a non-linear assumptions and develop a model. So that models are very complex models. So you can increase the model complexity in order to reduce the bias. Or you can add more features also to reduce the high bias situation. And or the third way in which you can reduce the high bias situation is by training the model for a longer duration of time. So these are some of the measures, remedies that you can use to overcome the high bias situation. If you are facing the high variance situation is the situation in which your test error is greater than your training error. You can overcome that situation by performing what it is called as the regularization. We are going to see what does it mean by the regularization in coming videos, and you can use more data or high number of training samples. So these are the symptoms and remedies for overcoming high bias and high variance situation. So this is all about bias variance trade-off. Thank you.